When an astronaut steps out of an airlock, they're not just leaving a spacecraft. They're leaving Earth itself. In that moment, there is no air, no warmth, no sound. Only an endless void. A place where one mistake, one tear, one forgotten latch could mean instant death. And yet, there they stand, floating above the world, bathed in sunlight older than civilization itself. Alive. It's not magic. It's a miracle of engineering, a symphony of science wrapped around the human body, the spacesuit, humanity's most personal spacecraft. Each time we see an astronaut on a spacewalk, that bulky white figure drifting gracefully against the deep black of space, it's easy to forget what's really happening inside that suit. We see the helmet, the gold visor, the patches and gloves. But what we're really looking at is a miniature life support system, designed to keep a fragile human alive in one of the most hostile environments ever encountered. A portable Earth. It must supply oxygen, maintain pressure, regulate temperature, remove carbon dioxide, manage sweat, and allow movement, all while surviving the brutal physics of space. And it has to do it for hours at a time. A personal spaceship. NASA calls it the Extravehicular Mobility Unit, or EMU. It's not just clothing, it's a vehicle. Every system inside that suit, from the air tanks to the cooling lines, is a piece of spacecraft technology. On the outside, it looks deceptively simple. White fabric, bulky limbs, a bubble helmet. But peel back the layers, and you'll find more than a dozen different materials, woven together like the layers of an onion, each serving a vital function. The outermost layer is made of orthofabric, a blend of Gore-Tex, Kevlar, and Nomex. It protects against micrometeoroid impacts and radiation, while reflecting heat away from the sun. Beneath that lies a pressure bladder, made of urethane-coated nylon. This is what actually keeps the oxygen inside and the vacuum out. But a sealed, pressurized layer creates its own problem. It behaves like a balloon. Try to bend your arm inside a pressurized tube, and it resists you. That's why the EMU has intricate joint bearings and restraint layers. Engineered wrinkles that allow astronauts to bend, twist, and work with tools while maintaining internal pressure. Each joint, each seam, each zipper has to hold up against a difference of more than 4 pounds per square inch. That's over 200 pounds of outward force pushing against the suit. And inside, it's not comfortable. Astronauts often describe it as working inside a stiff, inflated bubble, heavy, awkward, and punishing on the body. But in space, comfort is a luxury. Survival is the goal. Breathing in the void. The oxygen system inside the backpack, known as the Primary Life Support System, or PLSS, is the suit's beating heart. It provides breathable air, removes exhaled carbon dioxide, and even regulates humidity. Inside the helmet, air flows gently over the astronaut's face, sweeping away moisture and exhaled gases before cycling back through the scrubbers. The CO2 removal system uses lithium hydroxide canisters, the same kind that famously saved the Apollo 13 crew, to capture carbon dioxide and prevent poisoning. Meanwhile, a fan circulates the air constantly, ensuring no pockets of CO2 collect near the nose or mouth, because even a small buildup can be deadly. In the vacuum of space, there's no margin for error. Every molecule counts. A thermostat for the human body temperature control is one of the most overlooked and most critical functions of a spacesuit. In space, there's no air to carry heat away. When sunlight hits the suit, it can soar to 250 degrees Fahrenheit, but in shadow, it can plummet to minus 250. That's a 500-degree swing. To survive it, astronauts wear what might be the most advanced piece of clothing ever made, the Liquid Cooling and Ventilation Garment, or LCVG. It looks like a set of long underwear threaded with narrow plastic tubes. Cold water, pumped from a refrigeration unit in the backpack, flows through those tubes, carrying away excess body heat. It's a wearable climate system, tuned to the astronaut's metabolic rate. Without it, heat from exertion would build up, quickly causing dehydration, dizziness, and even heat stroke. Inside a vacuum. Every feature of the spacesuit, every screw and seam exists because space wants to kill you, and engineers refuse to let it. The suit isn't just equipment, It's a story of 60 years of trial, error, and human determination to walk beyond our world. Without it, a person in space would lose consciousness in less than 15 seconds. Within a minute, their blood would boil, their lungs would rupture, and their body would freeze solid in the shadow of Earth. This is the reality of space. It is not a gentle frontier. It is a vacuum, merciless, silent, and absolute. And so, to survive up there, astronauts wear what's essentially a spaceship shaped like a human being. The vacuum of death? Before we can understand how a spacesuit keeps someone alive, we have to understand what it's protecting them from. The vacuum of space isn't just no air, it's a total absence of pressure. Here on Earth, at sea level, the air around us presses in at about 14.7 pounds per square inch, a steady, invisible cushion that keeps the fluids in our bodies stable. In space, that pressure disappears. Instantly, if an astronaut stepped outside without protection, the gases dissolved in their blood would start to bubble out, just like opening a soda can. Their lungs would inflate, then collapse. Their saliva would boil. And while it sounds like they'd explode, they wouldn't. They'd simply fade away. It's brutal. But it's also what makes the spacesuit's job so extraordinary. The suit has to rebuild Earth, at least a small version of it, around the astronaut's body. Inside the suit, the air hums. Pumps whir softly. Fans move life through an artificial ecosystem the size of a backpack. To the astronaut, it's both comfort and confinement, a constant reminder that everything keeping them alive is right there, strapped to their body. Because in space, there is no rescue. There's only the system you bring with you, the symphony of systems. The primary life support system, that bulky white backpack, is often called the astronaut's lungs. But it's more than that. It's lungs, heart, kidneys, and skin. A complete support network that mimics the functions of a human body, but with wires, valves, and chemical scrubbers instead of organs. It circulates oxygen at just the right pressure, keeps the body's temperature stable, and removes the carbon dioxide that could turn the suit into a deadly chamber. Even the smallest detail is deliberate. In space, a fogged visor could mean the difference between completing a mission and losing orientation, or worse. The hands that touch the void. If you ask any astronaut what the hardest part of a spacewalk is, most will say the same thing: the gloves. They may look simple, but they are arguably the most complex part of the entire suit. Each glove has to provide flexibility, protection, insulation, and pressure retention, all while allowing the astronaut to handle delicate tools, twist bolts, and manipulate equipment in the vacuum of space. That's a lot to ask of something inflated like a balloon. Inside each glove, there's a careful network of tension lines and restraint layers that let astronauts move their fingers just enough to work, while resisting the pressurized force pushing outward. To maintain dexterity, NASA even custom molds gloves to each astronaut's hand, down to the millimeter. Still, the strain is enormous. A single 6-hour spacewalk can leave astronauts with blisters, bruises, and raw fingertips, the price of holding onto handrails while Earth spins silently beneath them. And yet those gloves are the only thing separating human touch from the infinite cold of space. Through them, humans have built space stations, repaired telescopes, and assembled the infrastructure of orbit, one turn of a wrench at a time. The unseen systems: water, waste, and air. There's one question few documentaries ask, but everyone wonders: what happens when nature calls in space? Because when you're sealed inside a suit for 8 hours, there are no bathroom breaks. Inside the suit, astronauts wear what NASA politely calls a maximum absorbency garment. Essentially, a highly engineered diaper designed for zero gravity. It's not glamorous, but it's vital. As for hydration, astronauts drink water through a small straw connected to a pouch mounted inside the helmet. It's held in place with Velcro, so it doesn't float away when the helmet is removed. It's these small human details that remind us, inside that billion-dollar shell of technology, there's still just a person, trying to do their job in one of the deadliest environments known to humankind. The mobility challenge: while the spacesuit protects life, it also fights movement. Each joint is pressurized, which means every bend of the arm or knee takes effort. On Earth, a fully assembled xEMU weighs about 280 pounds. In orbit, it's weightless, but not effortless. Without gravity, astronauts don't feel the mass, but they still feel inertia. Every motion has to be planned. Every twist and push generates an equal reaction in the opposite direction. So NASA designed the suit to allow astronauts to anchor themselves using handrails and footholds on the station's exterior. They move slowly, methodically, like underwater divers, except the ocean around them is an infinite vacuum, and the bottom is 250 miles below. The design of the lower torso assembly, the boots, legs, and waist, balances flexibility with rigidity. The boots lock into tethers, and the torso can pivot just enough to let astronauts reach critical tools without tearing the suit's fabric. Even the glove fingertips have tiny lights built in, helping astronauts see in the pitch-black shadows on the dark side of Earth. Every aspect of the design is a negotiation between safety and usability, between freedom and survival. Powering the cocoon all of this requires energy. Inside the PLSS, rechargeable silver zinc batteries provide power for fans, pumps, communication, and cooling systems. Each spacewalk is carefully timed around battery life, oxygen reserves, and carbon dioxide limits. When those readings start to fall, the astronaut must return. No exceptions. There's no rescue team waiting outside, no spare battery to swap. If the suit fails, the person inside fails too. That's why NASA and other agencies test these systems relentlessly, in vacuum chambers, underwater training facilities, and parabolic flights, long before anyone ever wears them in orbit. Every mission depends on the idea that once you leave the airlock, your suit becomes your world. The price of perfection, but even perfection, wears out. Most of the current suits, the same basic xEMU design used since the 1980s, are aging. Some components have been replaced, some upgraded, but the core systems remain largely the same. The suits that keep astronauts alive aboard the International Space Station are decades old, patched and maintained by... Space is unforgiving. Every solution creates new problems. And as humanity looks beyond low Earth orbit, to the Moon, to Mars, to deep space, the old suits won't be enough. Future explorers will need protection that's lighter, smarter, and built for alien worlds. Not just floating above Earth, but walking across new horizons. When the Apollo astronauts first set foot on the Moon in 1969, their suits were works of art. Handmade, custom-fitted, and designed in less than a decade. They were bulky, yes, but they worked. Those suits carried humanity from our planet to another world and back again. But that was half a century ago. Today, as we prepare to return to the Moon and eventually set foot on Mars, we face a new question. What does the next generation of life support look like? How do we design a suit that doesn't just survive space, but thrives in it? From the xEMU to the xEMU, NASA's answer begins with the xEMU, short for Exploration Extravehicular Mobility Unit. It's the successor to the decades-old xEMU, redesigned from the inside out for the lunar surface and beyond. The xEMU is lighter, more flexible, and modular, meaning its components can be swapped or upgraded depending on the mission. Unlike the xEMU, which was built for microgravity, the xEMU must handle dust, gravity, and long-duration wear on planetary surfaces. The Moon, for example, is covered in a fine, razor-sharp dust that clings to everything, a hazard Apollo astronauts called the #1 problem. It's abrasive, it's electrostatically charged, and it can damage joints and seals. The xEMU's outer layers are designed to resist this lunar dust while maintaining thermal protection and micrometeoroid shielding. Its lower torso assembly is far more mobile, allowing astronauts to kneel, climb, and even walk naturally on uneven terrain. The life support system inside the backpack has been completely reimagined, using modern electronics, compact plumbing, and advanced thermal controls. It's smarter, more efficient, and easier to maintain. But what really sets the xEMU apart is its modularity. It's not one suit for all people. It's a system that can be resized and reconfigured to fit a diverse range of astronauts. That means shorter prep times, better comfort, and fewer gender and body type limitations. A significant step forward for the next generation of explorers. It's a reminder that space exploration isn't just about technology, it's about people. And the people going to the Moon and Mars will be more diverse than ever before. Private space, private suits. But NASA isn't alone in this race. The rise of commercial spaceflight has brought new players, and new designs. SpaceX, Axiom Space, and Collins Aerospace are each developing suits for their own missions, combining NASA's legacy with sleek modern engineering. SpaceX's Crew Dragon suit, for example, is designed for launch and re-entry, not for spacewalks. It's slim, minimalist, and heavily automated, symbolizing a shift from heavy manual systems to integrated computer-assisted life support. Meanwhile, Axiom Space is building on NASA's xEMU technology for the Artemis program, creating suits that can operate on the lunar surface, lighter, more durable, and visually striking, designed for both function and flexibility. These commercial suits will mark the first time private companies provide the core life support technology for government astronauts, a monumental change in how space exploration is done. The suit is no longer just a government artifact. It's becoming a platform for innovation. Walking on Mars, the next frontier, but designing a suit for Mars introduces challenges unlike any humanity has faced before. The Martian atmosphere is less than 1% of Earth's pressure, filled with carbon dioxide. Temperatures can drop to minus 150 degrees Fahrenheit, and dust storms, vast planet-wide storms, can last for weeks. A Mars suit will need to survive gravity, radiation, static electricity, and chemical corrosion from iron-rich dust. It will also need to be self-sustaining, possibly for hours or days without resupply. That means new materials, flexible composites, sealed bearings, self-cleaning surfaces. It means life support systems that can recycle air and water with minimal loss. And it means artificial intelligence. Suits that can monitor their own systems, detect leaks or overheating, and adjust pressure or temperature automatically. Some researchers envision smart suits equipped with biometric sensors that constantly track heart rate, hydration, muscle strain, and oxygen consumption. In emergencies, they could even administer medication or signal distress autonomously. Imagine a future astronaut on the red plains of Mars, their reflection caught in a crimson horizon, guided by a suit that feels more like a partner than a tool. A second skin, intelligent and alive with data, the human cost of progress. But even as technology advances, one truth remains unchanged. Space doesn't forgive mistakes. Each new suit must be tested, refined, and proven in environments that mimic the real thing: vacuum chambers, thermal labs, and underwater simulations. Every valve and joint must survive radiation, cold, and the wear of movement. And the cost is immense in time, money, and human effort. Developing a single new suit can take years and cost hundreds of millions of dollars. Every screw, seam, and circuit must be perfect, because perfection is the only acceptable failure rate when human lives depend on it. Still, the drive to explore pushes forward, because for all its dangers, space also represents something more: the boundless curiosity that defines our species, and the spacesuit is the bridge between the impossible and the attainable. Beyond protection, a symbol of humanity. The spacesuit isn't just a machine, it's a symbol of exploration, of fragility, of human ingenuity. It represents everything we value about discovery: courage, persistence, imagination. When you see that white figure floating above Earth, it's not just an astronaut. It's every scientist, engineer, and dreamer who ever looked up at the stars and wondered, what if? It's humanity's declaration that even in the most hostile corners of the universe, life will find a way. Each new suit tells a story, not just of survival, but of identity. Because inside that helmet, beneath the layers of Kevlar and insulation, is a beating human heart, a reminder that we don't belong in space, but we go anyway. The future of the second skin. Looking forward, engineers are experimenting with radical new concepts, suits that blur the line between biology and technology. One design, called the biosuit, uses mechanical counterpressure instead of gas pressure. Instead of inflating like a balloon, it squeezes the body with advanced elastic materials, providing protection through tension rather than air. The result? A slimmer, more mobile suit that could revolutionize how astronauts move in reduced gravity. But it's not ready yet. The materials must withstand incredible strain, and sealing joints remains a major challenge. Still, the vision is compelling. A suit that feels less like armor and more like skin. A new generation of explorers, stepping across alien soil in suits that move, flex, and adapt as naturally as their own muscles. It's science fiction, on the edge of becoming science fact. In the end, a spacesuit is more than protection. It's a promise that wherever humanity dares to go, we'll bring a piece of home with us. Oxygen, warmth, safety, the comfort of breath, even in the vacuum of eternity. From the first Apollo suits to the next generation xEMUs, from the void of orbit to the red plains of Mars, these creations are our lifelines, our silent companions in the most unforgiving places we've ever known. The spacesuit isn't just how we survive space, it's how we become spacefaring beings. Because beyond the metal of rockets and the glass of capsules, it's the suit that defines our presence, one human at a time, against the endless black. The spacesuit is humanity's second skin, our armor, our cocoon, our home, carried with us wherever the stars may lead.